Hello everyone. Today I will talk about modular synthesis of reactive programs. This is a joint work with Kedar Namjoshi of Bell Labs and Richard Trefler from the University of Waterloo. A reactive program repeatedly interacts with its environment through streams of input and actions. Hardware circuits, communication protocols, and embedded controllers are some examples of reactive systems. In this work, we look at scalable synthesis of multi-process reactive programs from LTL specifications. Let us look at an example. Consider a simplified version of the dining philosophers problem. A few philosophers are seated around a table and they have only one fork. They need to share the fork so that every person can enjoy their meal. What is the correct protocol to achieve this goal? Well, to talk about correctness, we first need a formal specification. Consider these three properties. A. Every person is either eating or hungry. B. No two people eat at the same time. And C. Every person gets to eat perpetually. Observe that the first two are safety properties, while the third one, starvation freedom, is a liveness property. Let's say we were given a protocol for the dining philosophers problem. How do we check if it satisfies these conditions? For this discussion, we focus only on the safety properties. All methods outlined here extend to liveness properties as well, and we discuss them in the full paper. To verify a safety property, we can use a proof invariant, say theta, such that A. Theta holds for the initial state. B. If theta holds for a state S and there is a transition from state S to state S prime, then theta holds for S prime. And C. If theta holds for a state, then that state satisfies all safety properties. If the state space is finite, the search for theta can be automated using a SAT solver, where for each state S, we have variable theta S representing that theta holds at state S. And the conditions can be translated into propositional constraints. This gives us a propositional formula. The formula is satisfiable if and only if these three conditions hold for a given protocol. We can use a SAT solver to check satisfiability and thereby verify the correctness of the protocol. There is a folklore in the synthesis world. Every verification method can be inverted into a synthesis method. For reactive synthesis, we do the same and get the bounded synthesis framework. Given an LTL specification and a bound on the state space of a system, say N, the bounded synthesis framework constructs a protocol with at most N states such that it satisfies the specification. It converts the instance of the synthesis problem into a propositional formula such that the formula is satisfiable if and only if the synthesis problem has a solution. Then we can use a SAT solver to check satisfiability of this formula, thereby synthesizing a finite state protocol. Let us look at bounded synthesis for the dining philosophers problem. Suppose we are given a bound N on the shared state space and a bound N on local state space of each diner. We consider the shared state space as 1 to M and the local state space as 1 through N for each diner. Then the global state space is the Cartesian product of these. So if we have K diners, we take this product K times. We wish to find a transition system on this state space and an invariant theta such that the previously outlined proof conditions hold. As the state space is bounded for each pair S and S prime, we consider a variable T S S prime representing there is a transition from S to S prime and a variable theta S representing that S is in theta. Then as before, we convert the proof conditions into a propositional constraint and use a SAT solver. Observe that in the synthesis world, we are constructing the transition system and the invariant simultaneously. I tried implementing this method for the dining philosophers problem, and for 5 diners, it gave me a correct protocol in just a few seconds. For 6 processes, it took a bit more than a minute, and for 7, it took a couple of minutes. Is it fair to say that synthesis of multi-process protocols through bounded synthesis is feasible? Well, no. The method works up to 7 processes, but it does not scale beyond it. It simply times out on 8 or more processes. Scalability is a major challenge in synthesis of multi-process protocols. Let us try to understand this closely. The size of the state space grows exponentially in the number of processes. Remember that if there are k processes, this Cartesian product is taken k times. This exponential blow-up severely limits scalability. Tackling this challenge calls for new methods and insights. For this insight, we go back to our folklore, and this time draw inspiration from modular methods and symmetry reductions which have shown much success in scalable verification of multi-process protocols. Modularity at a high level is to consider each process separately. For modular synthesis, we synthesize a protocol for each process and then stitch these local protocols together. To achieve this, we first need a modular specification. The safety properties remain the same. For starvation freedom, consider the shared variable x. For k processes, say x can take values at least from 1 to k. Then we introduce constraints as a, if x is equal to I, then diner I eats eventually, and b, for some circular permutation on diners, say pi, if x is equal to I, then x is set to pi of I eventually. The specification here expresses that the shared variable can be treated like a token, which goes around the diners, and every diner who gets a token eats eventually. Therefore, the specification is a modular and stronger formulation of starvation freedom. From this high-level specification, we want to synthesize a protocol. For each diner, we define a local invariant theta with the properties a, theta is defined for the initial states, b, theta is preserved under local transitions of a process, c, theta is unaffected by interference, that is, theta is preserved under the actions of other processes, and d, if theta holds for a state s, then s satisfies all the safety properties. We use these local invariants for modular synthesis. For each individual diner, the state space is the Cartesian product of the shared state space and the local state space. That is, it's the product of 1 to m cross 1 to n. The transitions and invariants are defined per process. We construct variables and constraints as before, and then use a SAT solver. Observe that the number of variables in this encoding are polynomial in the number of processes. As you can see, there is a significant drop in the number of variables and constraints in this encoding. Here we can see a drop of multiple magnitudes when the number of processes increase. We were hoping that the reduction will dramatically improve performance. But we were surprised that modular encoding also does not scale beyond 6 processes. So we add another property, symmetry. Symmetry captures the isomorphisms in individual processes. With symmetry, we want to say that the local transition system of every process is the same. That is, if in process mi, there is a transition from s to s prime when the shared variable x is, say, alpha, then in process mj, there is a transition from s to s prime for an appropriate value of the shared variable. Here the value of the shared variable is pi of alpha, where pi represents the rotation from I to j. The transition symmetry implies that the proof invariants of each processes are also isomorphic. We force these symmetries into the SAT solver. The SAT solver gives us a protocol and it looks like this. There are 2 local states for every diner and they are all isomorphic. For diner I, one state is labeled hungry, represented by HI, and other is labeled eating, represented by EI. When the value of the shared variable is I, we can transition from hungry state to eating state. Once the diner is done eating, they set the shared variable to the next value. The shared variable then goes around all 5 diners. For this problem, our modular method can synthesize up to 42 processes in less than 17 minutes. Here is a figure summarizing the results. We tried to enforce symmetry in the non-modular case as well, but we see that it does not provide any significant improvement. We can conclude that the combination of modularity and symmetry is the key to tackling scalability. However, modularity and symmetry restrictions are a trade-off. By adding these restrictions, we limit our search to protocols with modular proofs. They allow us to scale. However, not all correct protocols have such proofs. We can remedy this by adding auxiliary states and synthesizing auxiliary transitions using the same method. In this work, we have outlined an initial exploration of ways to tackle scalability for synthesis of multi-process protocols. Our technique was motivated by the popular folklore, every verification method can be inverted into a synthesis framework. We borrow from modular methods and symmetry reductions to put forward a modular technique for bounded synthesis. Given the rich variety of program models, specification logics, and deductive proof systems, we believe that modular methods for synthesis promise to be a fertile topic for research. Thank you.